Hey everybody, welcome back to Complex Analysis, Math 350. Today we're going to be looking at an in-depth look at epsilon delta proofs. Now, epsilon delta proofs, they are a little bit tricky, but they are very, very important for those of you that are going on to Math 420, which is real analysis. And epsilon delta proofs are really at the crux of that class. So I want to make sure you guys are comfortable with it. So let's go ahead and get started. So we're going to start today back in calculus. Now this again maybe is something that you've seen in your Calc 1 course, but I want to go over it again and just make sure everyone's sort of on the same page with it. So let f of x be a function. So we say that the limit as x approaches x naught of f of x equals L if and only if for every epsilon greater than 0, there exists a delta greater than 0. So first of all, for those of you that have taken Math 322, this is an existence proof. It's a constructive proof. Okay. So in any case, if and only if for every epsilon greater than 0, there exists a delta greater than 0, such that, now we have a conditional, if absolute value of x minus x naught is less than delta, then the absolute value of f of x minus L is less than epsilon. Okay. So there's a lot of things to unpack here, so let's take it slowly, and if you have to, pause the video and kind of take it all in. But a couple of things. So first of all, remember that the absolute value can be interpreted as a distance. So the absolute value of x minus x naught is less than delta is saying that the distance between x and x naught is less than delta. Okay. And similarly, for the absolute value of f of x minus L is less than epsilon, this is saying that the distance between f of x and L is less than epsilon. Okay. Now, the reason why these are, the definition is the way it is, this is really sort of getting at the intuitive idea of a limit. So really quick, let's look at an example. Okay. So here's a function. It's a piecewise function, and notice we have a hole here at x equal to 2. Okay, there's the hole. So if we were looking at the limit as x approaches 2 of this function, okay, so hopefully if we, by just looking at the picture, hopefully everyone agrees that this limit's going to be right here at 3. Okay. Now remember, the intuitive idea behind the limit is the following. So we would say that the limit as x approaches 2 of f of x equals 3, that means that if we get really, really close to 2, so if x gets really, really close to 2, okay, the function gets really, really close to 3. Okay, and not only from the left side, but also from the right side. So if I get close to 2 from this direction, okay, my function gets really, really close to 3 from this direction. Okay, so that was the intuitive idea behind a limit back in calculus. Now, the problem with that, if you want to be very, very precise in mathematics, is this idea of closeness is it's not a well-defined thing, at least intuitively, right? Because my definition of closeness might be different than your definition of closeness. Just think about people's personal bubbles, right? And I think I said this in the last video, but some people have no personal bubble, whereas some people have, personal bubbles that are as big as a house. So the way that mathematicians made this idea of closeness precise is our epsilon delta definition. So if you really unpack this definition here, we're saying that if x is really close to x naught, then f is really, really close to L. So when you're thinking about epsilon and deltas, think about these as really small numbers. Really small numbers. Okay, because again, we want to get as close to x naught as possible, and at the same time we want f of x to be as close to L as possible. Okay, so that's how mathematicians made this idea of closeness rigorous. Okay, they're using the absolute value and then these really small numbers, epsilon and deltas. Okay, so hopefully that makes a little bit more sense, but let's actually see, how do we prove a limit by using the epsilon delta definitions. So I have some rough guidelines, and we're going to do some examples today, but I want to give you some guidelines to sort of structure how I'm going to be doing these things. So the way you approach epsilon delta proofs depends highly on what kind of function you're dealing with. If you're dealing with nice linear functions, then epsilon delta proofs usually aren't too terrible. But if you're dealing with quadratic functions, then they could get a little bit tricky, which we'll see an example of that today. Now keep in mind, what's your goal? Okay, So you're letting epsilon be greater than 0, and then your goal is to construct a delta that sort of captures the distances that we want. Okay, the distances in terms of, you know, your x and your x naught and your f of x and your L. Okay. Now, one thing to keep in mind, this delta is usually going to be some kind of expression that involves epsilons in some way. Okay. But it shouldn't involve x or anything weird like that. It can involve numbers like 2, 3, 4, constants like that. But it shouldn't involve x though. So delta should be some kind of like, so maybe delta is equal to epsilon squared, or maybe delta is equal to epsilon over 15. Okay. So this is what we're going to be seeking. Delta is usually some kind of number that depends on epsilon in some fashion. Okay. Now, when you go to prove a limit exists using this epsilon delta definition, usually what we do, and if you've taken 322, this is the backwards question. We usually start with this inequality here, and we use some kind of algebra to make it look like this. Okay, so we start with sort of what we want to prove. The distance between f of x and L is less than epsilon, and then we somehow use algebra to make that look like the distance between x minus x naught is less than some blah. And then whatever that blah is, that's what we let delta be, and then we're good to go. And then when we actually go to prove, we start with x minus x naught is less than delta, and then use our algebra to get f of x minus L is less than epsilon. So again, when you're trying to prove an epsilon delta proof, we usually start sort of backwards. You start with some scratch work. Okay, this is in your actual proof, but start with the end. Okay, and then somehow get the beginning out of it. Okay, and then when you actually go to write your proof, you kind of just go backwards. Okay, now this is, again, a rough guidelines. It depends definitely on what kind of function you're dealing with, but these are usually good starting points. Okay, a couple of things to keep in mind with absolute values, because again, we're manipulating these types of absolute values here. Okay, so you're going to want to be masters at absolute properties of absolute values. So a couple of things that I want you to keep in mind. Remember, the absolute value is always greater than or equal to 0. Remember, it's capturing a distance, so distance is always positive, or 0. If the absolute value of a number is 0, that means that that number has to be 0. Okay. Something that we'll probably use at some point, if you take the absolute value of negative 1 times x, the absolute value absorbs the negative sign, which should make sense, right? Because absolute values take negative things and make them positive. We have the triangle inequality, which we've already seen in a previous video. Now, things that we'll probably be using a lot today are these last three. Okay, so if you take the absolute value of a product of two numbers, then you can distribute the absolute value. And similarly, if you take the absolute value of the quotient of two numbers, you can sort of distribute the absolute value on the numerator and the denominator. Okay. And then lastly, like I've said a couple of times now, the absolute value of x minus a can be thought of as the distance from x to a. So just to show you a little picture, let's say this is x and this is a, then this distance here is the absolute value of x minus a. Okay, and we'll see pictures like that a lot today. Whoa. All right, so let's actually see an example now. All right, so our first example today, we're going to prove that the limit as x approaches 3 of minus 2x plus 2 is equal to minus 4, okay, which if you just substitute using the direct substitution property, you should see that, yeah, that's for sure the limit, right? And if you graph it, you should see that pretty easily too. Now, how do we actually prove it though? Let me erase this. Okay. So we're going to follow that strategy list that I gave you guys earlier. What we're going to do to prove this is we're going to start with some scratch work. Okay. So we're going to let epsilon be greater than 0. Okay, and remember our goal is to somehow find a delta, right? A delta that somehow involves epsilon in some way. Okay, so our goal, find delta. I always like to think about it's like you have some person on the street and he's like, hey, here's an epsilon. And then your goal is to say, ha, here's a delta. Because that's how limits works. If someone gives you an epsilon, you should be able to come up with a delta that will, that'll give us the distances that we want, those absolute value or those inequalities that we want. Okay, so let epsilon be greater than 0. Our goal is to find delta is greater than 0, some delta greater than 0. Now again, usually what we do is we sort of start backwards. So again, if you're thinking 322 or Foundations in Math or your proof class, this is the backwards question. Okay, so we start with sort of what we want. So we want that the absolute value of 2x plus 2, that's our function, minus negative 4, that's our limit. We want this to be less than epsilon. Okay? And now what we're going to do is we're going to manipulate this inequality to somehow get x minus 3, okay, which is coming from our limit part here because we're taking the limit as x approaches 3. We want to get that this somehow is less than something. I'll just put question marks for right now. Okay? Now let's see how we do that. So let's somehow manipulate our inequality here to get this. Okay? So let's go ahead and start simplifying the inside of this crazy absolute value. So we'll have minus 2x plus 2 plus 4 is less than epsilon. Let's add the 2 and the 4. It's less than epsilon. And now what we're going to do, we're sort of close to this, but we don't have a 2, we don't have a negative 2 in front of that x. Let's go ahead and divide, or we're going to factor out negative 2. And now once we do that, we should be a little bit happy because notice there's our x minus 3, which is sort of our end game, right? That's our goal. Well, not really our end game, but it's our goal for this part. So now we're going to use the property of absolute values. Remember, the product, the absolute value of a product is the product of the absolute values. Okay. Now what's the absolute value of negative 2? That's just 2. Whoops. Dividing both sides by 2, we get the absolute value of x minus 3 is less than epsilon over 2. Okay? And so that's exactly what we want, though, right? We want the absolute value of x minus 3 is less than something. So that something, this is what we want to choose as our delta. Okay. So this was our scratch work. Remember, for an epsilon delta proof, you're given an epsilon and you want to find a delta. So we just did the scratch work to actually find what delta we want. We didn't prove it. We didn't prove the limit is negative 4 in this case, but we have our delta though. So now let's actually prove it. Now again, our proof is going to be very similar to our scratch work, except everything's going to be flipped. But this is how we write it up in mathematics. So our proof. All right, so we're going to begin with let epsilon be greater than 0. Okay. And let's let delta be what we found earlier, epsilon over 2. Okay. Then, and now again we're going to sort of retrace our work, then if the absolute value of x minus 3 is less than epsilon over 2, we have 2 times the absolute value of x minus 3 is less, and I did not mean to put a less than or equal to there. Get out of here. Then multiplying both sides by 2, we have 2 times the absolute value of x minus 3 is less than epsilon. Remember, we got 2 out of the absolute value of negative 2. Okay, redistribute the negative 2. And then I already forgot, what did we do to get minus 2x plus 6? We rewrote 6 as 2 plus 4. And now finally we can rewrite our inequality so that we have exactly what we want. Minus 2x plus 2 minus negative 4 is less than epsilon. And remember, this is our function f of x. And then this was our L here. Okay, so we've proved that given an epsilon greater than 0, there's a delta, in particular this delta was epsilon over 2, such that if the distance between x and 3 was less than delta, or epsilon over 2, we had that the distance between our function and the limit is less than epsilon. So again, sort of the intuitive idea behind this is that if x gets really close to 3, f of x gets really close to L. Okay, so let's see another epsilon delta proof, and this one has actually a little bit more spice, and we'll see why in a second. But in any case, we're going to prove that the limit as x approaches 3 of x squared minus 1 is equal to 8. Now this is another example where if you just use the direct substitution property, you'll see that this limit is 8 because 3 squared minus 1 is equal to 9 minus 1, which is 8. But how do we prove that precisely, though? How do we use the epsilon delta definition? So again, we start in the same way that we did the previous problem, but then we'll see there's a little bit of a twist that we have to do. Okay, so we're going to start with our, again, this is kind of the backwards question from 322. We're going to start with, well, assume that x squared minus 1 minus 8 is less than epsilon. Okay, and then we're going to somehow try to get it to x minus 3 is less than, again, some blah, or some question mark. Okay, so let's see how that goes. Let's try that. So let's simplify our inequality here. And actually, let me just emphasize really quick, guys, this is, again, the scratch work. This is not the proof. Scratch work. Okay, so using a little bit of arithmetic here, we can take our inequality and rewrite it as x squared. So minus 1 minus 8, that's minus 9, is less than epsilon. And now, what do we do at this point? So for those that are really, really good with their factoring, notice that x squared minus 9 can be rewritten as x plus 3 times x minus 3. Okay, and then using our, well, first of all, this should make us a little bit happy because remember our end goal is somehow getting an x minus 3, right? Well, so here, we should be a little bit happy, okay? However, we're actually kind of hitting a roadblock in a way because now if we use our absolute value property, remember the absolute value of a product is the product of the absolute values, we get this. Now you might be really tempted to say, well, this means that x minus 3 is less than epsilon over x plus 3, and you might be saying, well, let delta be this thing. But remember, delta can't depend on x. Delta can only have epsilons in it, or numbers, or constants. It can't have x. Remember, the limit definition doesn't say that delta depends on x, right? Delta should only depend on epsilon. So we're kind of hitting a snag here because we can't simplify this anymore. We can't just get rid of the x plus 3. I mean, that'd be kind of nice, but that would be very, very against the rules of math. So what do we do in this case? So we're kind of, again, we're sort of at a roadblock here. But old question. What do we do with this thing? Okay, so this is where we pull a fancy trick out of our sleeves. And it's not really a fancy trick, but keep in mind, remember our original goal is to find this delta such that the distance between x minus 3 is less than delta, okay? Remember, that's our goal. We're trying to find this delta, right? And keep in mind, remember, the intuitive idea behind a limit is that delta and epsilon, they're really, really small numbers, right? Because we're trying to let x get really, really close to 3, and we're trying to let f of x get really, really close to L, okay? So epsilon and delta, they're usually really, really small numbers. Okay, so what we're going to do is we're just going to pick a really small number. Delta is really small. What's a number, a really small number that you can think of? And we're going to go with, and usually this is what is commonly done, we're going to go with delta equal to 1. So suppose, just for instance, let's suppose that delta is equal to 1. Okay, now what would this be saying? If we have that the distance between x and 3 is less than delta, or 1, okay, let's draw this on a number line. We have, let's say, 3 here, okay? And if the distance between x and 3 is less than 1, that means that x has to fall somewhere over here. Let's say x is right here, okay? Now let's compare that with x plus 3 here. Remember, the absolute value of x plus 3, you can interpret this as the distance between x and minus 3. Whoops. So this here is distance of x and minus 3. Okay, so let's draw in minus 3. So minus 3 is going to be, let's say, over here. Okay, and so worst case scenario, x, like in terms of distance between x and minus 3 here, worst case scenario, x is all the way over here. Okay, so we know that the distance between, if delta is 1, and so the distance between x and 3 is less than 1, we know that at worst that the distance between x and negative 3 has to be less than, so in this case this will be 7. Okay, because what is this distance right here? If x was all the way here, sort of at the border of 4 here, it's almost 7 away from minus 3. So the worst we could do is 7. Okay, so now we're going to use this information. Keep this in the back of your head. Delta here, if delta was 1, which is, okay, it's somewhat realistic because, again, delta is supposed to be really small, we would get that the distance between x and minus 3 is less than 7. So going back to our question marks over here, erase, we can improve this to say, well, the distance between x and negative 3 was less than 7, so we'll have that. Let's see. We can really replace this with a 7. And so, simplifying, we'll get x minus 3 is less than epsilon over 7. Okay. Boom. So now we've isolated our x minus 3, and we got it less than something that doesn't have any x's or anything in it, and only has epsilons. Now we come up with a little conundrum, though. So we supposed here that delta was 1, and here we have another candidate for delta, epsilon over 7. Now to ensure that everything goes to plan, that the distance between x and 3 is less than epsilon over 7 here, or the absolute value of x minus 3 is less than epsilon over 7, and to ensure that the distance between x and negative 3 is less than 7, okay, we're going to choose delta not to be 1 or epsilon over 7. We're going to choose delta to be the minimum of epsilon over 7 and 1. Okay. Now this might be weird, but what this is saying is that we're saying that you have two numbers here. We're going to let delta be the smallest of them. And the reason why we're letting delta be the smallest of these two numbers is we want both of these inequalities here to hold. Okay. If delta is less than 1, then we know that the absolute value of x plus 3 has to be less than 7 from our little picture here. On the other hand, if delta is less than epsilon over 7, okay, or equal to, then we know that this inequality holds. Okay, so this is going to enable us to actually write a rigorous proof. Okay, so this is the trick. Now I want to make a quick comment. We chose delta equal to 1. Remember, that was something we just sort of pulled out of thin air. 1 is a relatively small number. You could have picked another number, though. You could have picked, let's say, delta equal to, I don't know, a half, or delta equal to 0.1, or delta equal to 0.00001. Okay, and that would have adjusted your delta here a little bit. Okay, so there is a little bit of arbitrariness here. I picked 1 because it was an integer, and it's sort of the smallest integer that we have, right? Other than 0. The smallest positive integer that we have is the number 1. Okay, so in any case, this is the delta that we want to pick. So now let's write up the proof. Okay, so again, like all epsilon delta proofs start with, we're going to let epsilon be greater than 0. Okay, and now we're going to use the delta we just defined earlier and let delta be equal to the minimum of epsilon over 7 and 1. Okay, now again, the reason why we're doing this, remember, the epsilon over 7, that's for the absolute value of x minus 3 being less than epsilon. Okay. Whoops, I'm sorry, epsilon over 7. So that's for that inequality. And then the 1 here was to make sure that the distance between x and minus 3 was less than 7. Okay, so keep that in the back of your heads. We're going to be using that in a second. Okay, so let epsilon be greater than 0 and let delta equal the min of epsilon over 7 and 1. Okay, so suppose that x minus 3, so the distance between x and 3 is less than delta. And remember, what we want to show eventually is that the function minus our limit is less than epsilon. or the distance between our function and our limit is less than epsilon. Okay, so now let's start to work this. So now what we're going to do is we're going to multiply both sides by 7. Okay, and now remember, delta is less than epsilon over 7. So we know that this side is less than epsilon, 7 times epsilon over 7. I should say here, let me be more specific, or more careful here, because delta is the minimum, right? So it could be epsilon over 7 or it could be 1, but it's the smaller of the two. So this right here is less than or equal to 7 times epsilon over 7, which is epsilon. Now on the other side though, remember 7, because of how we're choosing delta here, 7 is greater than the distance between x plus 3. So on the left-hand side here, we can write, well, x plus 3 times x minus 3 is less than 7. Okay. So sort of chopping this inequality a little bit, what do we have? We have that x plus 3 times x minus 3 is less than epsilon. Okay, so that's taking this piece and sort of this piece here, although I have a really weird epsilon there. Sorry about that. Okay. And now we're sort of going to work backwards now. So let's combine everything on the left-hand side here. So this will be, again, using our properties of absolute values, this will be x squared minus 9 is less than epsilon. And remember, we want our function minus the limit, right? So we're going to rewrite this as x squared minus 1 minus 8 is less than epsilon, and then we're good to go. This is f of x minus L is less than epsilon. Okay. So when your functions are a little bit more complicated, in this case we had x squared minus 1, sometimes when you're doing epsilon delta proofs, you're going to have to pull these kind of tricks out of your sleeves. Okay. You're going to have to sort of think a little bit, well, if delta is really small, let's say 1, then what is that going to tell us? Okay, so keep this trick here, this is a trick, keep this trick in the back of your mind. Okay, now epsilon delta proofs in complex analysis work very, very similar to how they would in calculus. Okay, so the guidelines that I gave you and the tricks that we just sort of talked about, they are still good and noteworthy, and I recommend them. Okay, now like we said in the last video, here's the definition of the limit. So suppose f is a function and z naught is an accumulation point of g. Remember, an accumulation point here, this is allowing us to get as close to z naught as possible, or as we want. And suppose that w naught is another complex number. So we say that the limit as z now, because we're in complex land, the limit as z approaches z naught of f of x is equal to w naught if and only if, for every epsilon greater than 0, we can find a delta, so there exists a delta, so that if the distance between z and z naught is less than delta, then our function, or the distance between the function and w naught, is less than epsilon. Okay, and if we can find this for every epsilon, we would say that, well, the limit of f of z is equal to w naught. Oops. Okay, so again, similar definition that we had in calculus, except we're complexifying it, which is not a word, but we'll make it a word by the end of this series or this class. All right, so let's see an example. So let's prove that the limit as z approaches I, okay, the complex number I, of 3z plus 1 is equal to 3i plus 1. Now again, here's another example. If you were to use the direct substitution property, you would see, well, if you plug in z is equal to I, you do get 3i plus 1. So this should make sense that this is the limit. But again, how do we prove it precisely? We have to do a little bit more work. Okay, so we're going to proceed. Let's do our scratch work. Okay, so we're going to let epsilon be greater than 0. And keep in mind, remember, we're thinking about epsilon as a really small number because we're trying to sort of limit distances or make distance small. Distance is small. And then we're going to suppose that 3z plus 1, so that's our function, minus the limit, is less than epsilon. Keep in mind, remember, what are we trying to generate? We're trying to generate that delta. Okay, so let's suppose that this is true. Okay, so let's simplify our left-hand side here. So this will be 3z minus 3i. The 1's cancel out. It's less than epsilon. Now we can factor out a 3. And looky what we have here. Divide both sides by 3. And we have that z minus I is less than epsilon over 3, which if you think about it, if we look at our limit here, that's what we want, right? So this is what we want delta to be. Okay, so now let's actually prove this. Remember, this is just the scratch work. So to prove the limit, we're sort of going to go backwards now. So proof, pinkies up everyone, let epsilon be greater than 0, and, I don't need a comma there, and delta equal to epsilon over 3. And let me just double check, that's what we said over here, right? Yeah, epsilon over 3. Okay, so if the distance between z and I is less than delta, which equals epsilon over 3, okay, then we have, and again, we're just going to try to reconstruct. Our end game is to get that f of x, whoops, I'm sorry, not f of x, f of z. We're in complex land. We're trying to get that f of z minus L is less than epsilon. Okay, so if z minus I is less than delta, which is epsilon over 3, let's rework it backwards so that we get this inequality here. Okay, so let's multiply both sides by 3. We'll get 3 times the absolute value of z minus I is less than epsilon. Okay, let's distribute the 3 inside. So we'll get 3z minus 3i is less than epsilon. Now this isn't our function yet, so what we're going to do is we're going to add and subtract 1. So we're going to 3z plus 1 minus 3i minus 1. Okay. And now what do we do here? We'll recognize that this just becomes 3z plus 1 minus 3 plus I. I'm sorry, 3i plus 1. I's look very, very similar to 1's. 10. Okay. In any case, and then now we just recognize, well, that's f of x. That's our L. I'm sorry, not f of x. That's our f of z. Okay, that's our L. So we do, in fact, have the inequality that we want there. The absolute value of f of z minus L is less than epsilon. End of proof. Boom. So again, notice works very similar as it did back in real land or calculus land. But we've just complexified it a little bit. Okay, so let's look at, again, a similar example that we saw. And remember, when we did the x squared example, it was a little bit more complicated. We'll see it's pretty much the same idea here. So let's go ahead and prove that the limit as z approaches 4 plus I, so let me go ahead and draw our complex plane. So 4 plus I would be 1, 2, 3, 4. Here's 1. It'd be this point right here, 4 plus I. So the limit as z approaches 4 plus I of z squared is equal to 15 plus 8i. Okay. Now, one thing I want you to notice, again, if you use the direct substitution property, 4 plus I squared is equal to 15 plus 8i. Okay. Do the arithmetic on your own, FOIL that out, you will see that that is true. Okay, but try it on your own though. Verify that. But how do we prove it though? So again, we're going to use our epsilon delta tricks. So we're going to go ahead and start with our scratch word. Okay. Let epsilon be, again, a small number. Okay. And what we're going to do, again, we're going to start with sort of what we want to show. Suppose that z squared minus 15 minus 8i, okay, so that's our f of z minus L there, is less than epsilon. Okay, and we want to somehow get our z minus 4 plus I. Okay, so our goal is to get something that looks like z minus 4 plus I is less than blah. Okay, so how do we do that? Well, let's recognize that 15 plus 8i is equal to 4 plus I squared, so we can rewrite this as z squared minus 4 plus I squared. Okay, and now we have the difference of two squares, so we can factor this as z plus 4 plus I and z times z minus parentheses 4 plus I. Okay, and now we should be sort of happy, right? Again, kind of like in the real case, we have absolute value z minus 4 plus I here, okay? But we also have this extra factor of z plus 4 plus I, okay, which we don't want. Remember, we can't just divide that over and say delta is equal to that because we have z's here, okay? So we're going to have to do the same trick that we did last time. So suppose that z minus 4 plus I, let's suppose that delta was equal to 1. Okay, so if the distance between z and 4 plus I, and let me not lose my parentheses there, is less than 1, or delta in this case, what do we actually get? So that means that if we draw a circle of radius 1, okay, because again, remember we're in complex land now, this means that z has to be within the circle here, okay? Well, let's think about, well, what about here? What does this inequality mean? This inequality here represents the distance between z and minus 4 minus I. So if we draw minus 4 minus I, okay, so here's minus 4 minus I. What do we know about the distance between x and this point here? Okay, well, worst case scenario, the farthest x could be would be somewhere close to this boundary point here. That's the worst that x could be. Okay, any other point would be closer than that. All right, so to figure out how far x is away from, I'm sorry, not x, how far z is, how far z is away from minus 4 minus I, let's go ahead and use a right triangle. So let's suppose that this is 2i here. Let's draw a right triangle. Okay, let's pretend like that's a good right triangle. Okay, there we go. So this height here, this will be, let's see, 2 plus 1, that's 3. This length here will be, let's see, 1 plus 4, that's 5, plus another 4, that's 9. Okay, and so let's see this distance here. Whoops, let me not use delta. Let's say d. So d squared is equal to 9 squared plus 3 squared. This is equal to 81 plus 9. So let's see, d is 90. Whoops, d squared is equal to 90. Okay, so d is approximately, let's see, well, it's equal to square root of 90. And let's see, square root of 90. Let's just say this isn't 10 on the nose, but this is less than 10. Okay, and remember, we're just trying to get less thans everywhere, right? So this is approximately less than 10. So we know that if delta is equal to 1, the point of this is, if delta is equal to 1, then we have that the absolute value of z plus 4 plus I is less than 10. Okay, using again this Pythagorean, well, the Pythagorean theorem in this triangle. So going back to our inequality, let's replace this with a 10, and then we become super happy. So our inequality will simplify to z minus quantity 4 plus I less than epsilon over 10. Now again, like we did in the other example, we have a conundrum. What do we let delta be? Because we have two candidates. We have 1, which gave us this inequality here, and we have epsilon over 10, which gives us this inequality. So to make sure that both inequalities hold, we do the same trick as we did last time. Let delta be the minimum of 1, whoops, wrong brackets there, the minimum of 1 and epsilon over 10. Okay. And if we do that, that's going to ensure that this absolute value here is less than 10 and this absolute value here is less than epsilon over 10. And that'll help us actually prove this. Okay, so let me add really quick. Okay, so let's actually prove this. So proof. Okay, again, we're going to start with let epsilon be greater than 0. And let's let delta, after doing all that work, we're going to let delta be the min of 1 and epsilon over 10. Now remember, the 1 here is allowing us to say that the absolute value of z plus 4 plus I is less than 10. And then epsilon over 10 here is allowing us to say that the absolute value of z minus 4 plus I is less than epsilon over 10. There we go. Okay, so just keep those in the back of your heads because we're going to use those in a second. So let epsilon be greater than 0, let delta be the min of 1 and epsilon over 10. So suppose that the distance between z minus 4 plus I is less than delta. Okay, so again, since delta is the min of 1 and epsilon over 10, we know that delta is less than or equal to epsilon over 10, so we have the following inequality. Okay, now multiplying both sides by 10, we get, well, very, very nice, epsilon on this side, now we have a 10 on this side. Well, remember that since we're picking delta to be less than 1, remember, we know that the distance between z and negative 4 minus I is less than 10, so we can say, on the other hand, this is greater than z plus 4 plus I. Let's pretend like I can actually write this properly. Z plus 4 plus I, there we go, times absolute value of z minus 4 plus I. Okay. And now combining these parts together, we now have that the absolute value of z plus 4 plus I, times the absolute value of z minus 4 plus I is less than epsilon. We're going to do our backwards algebra. We can simplify the left-hand side to say that this is z squared minus 4 plus I all squared. But remember, 4 plus I squared, that was equal to 15 plus 8I. And then boom, that's exactly what we wanted. Now this is our f of z minus L is less than epsilon, and we are GT2G. Good to go. All right, so that's it for epsilon delta proofs. We'll get some more practice with this in class, and I will see you all then.